All right, we're at the point now where we want to use derivatives, now that we know what a derivative is. We want to use derivatives to help us get some information about what the graph of a function looks like. So we're going to focus on increasing and decreasing. So from a previous course, you might have already been told what it means for a function to be increasing or decreasing. So suppose S is some interval which is in the domain of our function, and that the function is defined for every value of x in that interval. Then we're going to say that our function is increasing on that interval if and only if f of a is going to be less than or equal to f of b for all a and b which are elements of S, which means for all a and b that are in that interval such that a is less than b. A lot of times in mathematics, it helps to reread things. You're constantly rereading, making sure you understand everything, because every word, every phrase is important. If it wasn't, it wouldn't be in there. So let's look at an example. What they're saying here is, let's say we have some interval, and let's say this is a and this is b that's in the interval. If a function's increasing, then that means that f of a, let's say here's f of a, is going to be less than or equal to f of b, and then if f of b is over here, for any a and b in that interval where a is less than b. So in other words, and by the way, it has to be defined for all x, which means our function is going to be continuous. So no matter what's going on here, that would dip down a little bit. But it could be going like that, it could be going like that, it could be going straight for a little bit and then up. But our function's increasing if the output at b is going to be greater than or equal to the output of a for any a and b in that interval where a is less than b. And on the other hand, decreasing is going to be just the opposite, and that would be that f of a is greater than or equal to f of b, and that would just switch the order. So that would say that f of a is going to be higher than f of b. So then our function is going to be decreasing or going down. Now the one thing I don't like about these definitions, because of this less than or equal to, greater than or equal to, well, then technically a constant function, like how about y equals 3, they would say, according to this definition, would be increasing and it would be decreasing. And I would say it's neither. So keeping that in mind is important. Now let's tie this into derivatives. So our function's increasing on an interval S if f prime of x is greater than or equal to 0 for all the x's in that interval. So for every x value in that interval, the derivative has to be non-negative. If the derivative is positive, so if we exclude equal to 0, then we say that our function is strictly increasing on that interval. So it doesn't level off at all. So for example, if you think of y equal x cubed, that's a good example. You would say, well, that's increasing everywhere from negative infinity to infinity. But at 0, if I drew this a little better, the derivative at 0 is 0 because we have y equals x cubed. Y prime would be 3x squared. And so y prime of 0 equals 3 times 0 squared, which is 0. But yet our function is still increasing everywhere. So that's why they include, f prime could be greater than or equal to 0. Once again, though, that neglects the issue of a horizontal line. And then similarly, we could say that a function is decreasing if the derivative is less than or equal to 0 for every x in that interval. So in other words, it's not positive. And then we'll say that it's strictly decreasing if the derivative is strictly negative for every x in that interval. Sometimes you'll see the phrase monotone referring to a function, and we'll say a function's monotone if it does not change from increasing to decreasing, or vice versa, on a specific interval I. All right, so this doesn't really help unless we jump into a couple of examples. So let's go through two examples. let's find the intervals where this function is increasing or decreasing. So the first thing we're going to do is we're going to find the derivative. And that's easy enough. Negative 3x squared plus 6x. And now we want to find out the stationary points where the derivative is 0, where the tangent lines are horizontal. So we're going to set our derivative equal to 0 and use techniques that we've learned in the past. So we can factor out a negative 3x, and we're left with an x minus 2. Okay, so that tells me that the derivative is 0 when x equals 0 and when x equals 2. So what we want to do is we want to make a little line here, and we want to put those two values on there. Now, if you think of this as a number line, normally we put the numbers underneath. I'm actually going to put the numbers above. So these are going to be the x values. When x is 0, when x is 2. And down below, I'm going to put the values of f prime. Now we know that f prime is equal to 0 when x is 0, and it equals 0 when x is 2. Get an arrow here to help. All right, I know there's no other zeros for the derivative. So that means that the derivative, it's down a little bit, the derivative is going to be either negative or positive in this section, and then negative or positive in this section, and negative or positive in this section. I also know that it's not going to be changing from positive to negative or negative to positive in any one of these sections. It's going to be consistent throughout. And I know that because if f prime actually was negative for some values and positive for other values, then there'd have to be another 0 in here. And I know that there's no other zeros for the derivative. So all I need to do is pick an x value that's in this interval, so from negative infinity to 0. Let's say I pick negative 1, for example. I'm going to plug that into f prime and see what kind of an answer do I get. Do I get a negative answer or a positive answer? And any other value I would have picked for x is going to give me that same answer, either a negative or a positive. So I just have to test one number in this section, in this interval here. So I'm going to pick negative 1. Now you can plug it into the original f prime. I think it's easier to plug it into the factored form. And the reason being is I don't care what the specific answer is. I just want to figure out, is it going to be a positive or a negative answer? So if I plug negative 1 in here, this is going to give me a positive. And when I plug negative 1 in here for x, this is going to be a negative. So I'm going to get a positive times a negative, which means f prime is going to be negative. So if I had picked any other number, negative 2, negative 15, negative 1087.8, doesn't matter. I'm still going to plug it in for x here, and I will wind up getting a negative. All right, now let's pick a number between 0 and 2 and figure out what f prime is. So obviously 1 would be a logical choice. So if I plug in 1 for x here, I'm going to get a negative. Plug 1 in for x here, I'm going to get a negative. When I do a negative times a negative, I get a positive. So f prime is always going to be positive between 0 and when x is between 0 and 2. And then finally, I'll pick a number greater than 2. How about 4? Plug in 4 here, I get a negative. Here I'm going to get a positive. Negative times a positive is a negative. So now what does that tell me? This tells me that if f prime is negative, that means, let me draw a picture here. If f prime is negative, that means the slopes of my tangent lines are negative when x is less than 0. And then when x equals 0, all of a sudden the slope of my tangent line is 0, which means it's horizontal. And then after that, after 0, for a little bit of time at least, my derivative is positive. That means the slopes of my tangent lines are positive. And then when x equals 2, all of a sudden the slope of my tangent line is 0 again. And then when x is bigger than 2, my derivative is negative, so that means the slopes of my tangent lines become negative again. So what is that telling me? So looking at this sign chart, because f prime is negative and then 0, and then positive, I know my function f, and this represents my function f, is going to be decreasing until I get to x equals 0. And then that's going to be a local minimum. And then between 0 and 2, my derivative is positive, so I know that my function is increasing. And then when x equals 2, my derivative is 0 again, so that's going to be a local maximum. And then when x is bigger than 2, my derivative is negative, which tells me my function f is decreasing. So looking at the signs of f prime tells us a lot about the shape of our graph of f. So we know that we're decreasing, increasing, and decreasing. This is a local minimum, and this is a local maximum. So let me fill in all that information. Move that up there. All right, so now we can say that f is increasing when x is between 0 and 2. And in IB, they like to include the endpoints there, so we'll include them. If you're using interval notation, then we'd use the brackets 0, 2. Remember, if you're not going to include something, you have a reverse bracket in IB. All these years in math, you've learned to just use a parenthesis. IB uses reverse brackets. Okay, so, or we could say 0 and 2. All right, and then f is decreasing from when x is less than 0, let's say less than or equal to 0, they include the endpoint, and then when x is greater than or equal to 2. So with interval notation, we would say negative infinity to 0. We never include the negative infinity. And 2 to infinity, union with 2 to infinity. Okay, so you could use inequalities or you can use interval notation, whichever you prefer. And then we also know that we have a local minimum here, because our tangent lines point to this. Our tangent lines were decreasing. Our tangent line slopes were negative, which means f is decreasing, then it levels off, then it's increasing. So there's a local minimum. And then if f prime is positive, f is increasing, levels off, and then is decreasing. So that tells us we have a local maximum at that point. All right, so that's how we use a derivative to help analyze a function, and specifically when a function is increasing or decreasing. Let's look at one more. A little more complicated. Find the intervals where this function is increasing or decreasing. All right, so start off just like before. Find the derivative, set it equal to 0. Find the zeros of the derivative, make a sign chart, plus minus chart, and then figure out where, that'll tell us where our function f is increasing or decreasing. And we have to use the quotient rule here. So the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. All right, so this fraction will be 0 when the numerator is 0. So let me distribute combine like terms. I've got 2x squared plus 4x minus 6, 4x, so minus 4x squared. I'm going to get a negative 6x plus 4x is a negative 2x, but I'm subtracting, so plus 2x. And then I'll get a negative 6, but I'm subtracting, so plus 6. So I have 0 is equal to negative 2x squared plus 6x. If I did that correctly. Hopefully I did. I'm pretty sure I did. So let's factor it. I can factor out a negative 2x. And then I'm left with an x minus 3. Looks like I put a decimal point there. By the way, hopefully you've hit pause and try and work through some of this on your own. So that means that x is equal to 0 and x is equal to 3. So those are my zeros, which could represent local minimums or maximums. I specify could represent. More on that later in the next lesson. All right, so let's make our plus minus chart. And we have 0, and we have 3. These are my x values. It's really important to label this so somebody looking at it knows exactly what this sign chart is for. Later on, we'll do a sign chart with a second derivative. That'll tell us about concavity of a function. So we have f prime here. Let's use my favorite. So the derivative is 0 when x is 0, and the derivative is 0 when x is 3. That's the worst arrow I've ever drawn this morning. Okay. So let's pick a number in this section. So how about -1? Plug that into your derivative. Now, I mentioned plugging it into the factor form. Remember, this is the derivative. This stuff here is just the numerator. So we have to be a little careful. Let's think about this. When I pick a number, now, whatever I plug in here, this value, when I square it, is going to be non-negative. So I know that I don't have to worry about the denominator being negative. So I can actually just plug it into the numerator, and the numerator is this stuff here, simplified. So I'm just going to use this right here. So when I take -1 and plug it in here, I get a positive times a negative is a negative. So f prime is negative. Kind of looks like what happened in the last example. But be careful. 0 to 3, let's pick, I don't know, how about 2? Plug in 2 here, I get a negative amount, and a negative amount gives me a positive amount. That tells me that f is increasing in that interval. And then I'll pick a number bigger than 3, how about 4? Plug it in, I'm going to get a negative amount here, positive amount. Negative times a positive is a negative. And remember, we're dividing by a positive, so that still makes it negative overall. All right, so this is telling me that f is decreasing. Here it's increasing. And here it's decreasing. And also, because f prime is -0 positive, that means the slopes of my tangent lines, we've got negative slopes, 0, positive. That tells me that this is a local minimum. And then at 3, before 3, f prime was positive, so my slopes were increasing, and then 0, and then decreasing. So I have a local minimum, or local maximum at 3. All right, so we've got a lot of information. However, we're not done. I'm not ready to write where it's increasing and decreasing, because this function was a little more complicated. What's the domain of this function? Well, we know we can't divide by 0. So anything that would make the denominator 0 is not in the domain. It's either going to be a vertical asymptote or a hole. So we need to look at that. So we can factor this. That's x plus 3, x minus 1. And the numerator we can't factor. If you could cancel one of those factors, that would represent a hole in the graph. So this tells me that I have vertical asymptotes. See, all that stuff we learned in pre-calc is coming back now. Vertical asymptotes at x equals -3 and at x equals +1. So that's not in the domain of my function. So now I have to take that into account when I'm talking about increasing and decreasing. So I know that x cannot equal -3. So f is decreasing from -infinity to 0, except at -3, because my function's not defined. All right, so now let's go ahead and specify that. So f is increasing. By the way, notice that I keep writing f or f prime, because we want to make sure that we understand which function we're referring to. The derivative itself is another function. So f is increasing between 0 and 3, except at 1. So I'm going to use interval notation. So between 0 and 1, not including the 1, union with 1 and 3, including the 3. Now that may seem a little weird using those brackets for IB, and I agree. So I guess if we want to use inequalities, we could say 0 less than or equal to x less than 1. And then from 1 less than x less than or equal to 3. So if you like that better, go with that. I just want you to be familiar with what that should look like. All right, and then f is decreasing. So that's from negative infinity. And remember, we have to exclude x equals negative 3. That's not in the domain. So we're going to go negative infinity to negative 3, not including those, union with, and then negative 3 to 0, include the 0, don't include the negative 3, union with 3 to infinity, including the 3. Using inequalities, what would that say? Let's see, negative 3, so we would say x is less than negative 3. And then between negative 3 and 0, including the 0. And then from greater than or equal to 3. And there we go. And if you want, you can go ahead on your calculator and take a look at that and verify. But you can see how much insight that gives us. And so it's really important to be able to master the sign chart for f prime, and then make sure you understand what that's telling you about your function f. All right, some homework problems, 13C, starting on page 324.